Hello everyone. Can you hear me okay? Could somebody turn their mic on just to... Yeah, great. Good, thank you. Hi, I'm Gerard Stewart. I'm the communications coordinator for the NFM research programme, and welcome to our 23rd webinar in this series. Actually, it's the penultimate one. And yeah, the aim of the series is to help researchers and practitioners share knowledge and experience in NFM. Today we were to have Martin and Donald from the University of Manchester presenting. Donald has actually got a new baby, so a new baby girl. So Martin has been left holding the baby, if you'll excuse the phrase. Before we start, a couple of housekeeping points. Please would you turn off your microphones if they're not already turned off, keep them off, and keep your cameras off to avoid distractions. There is a chat function, so please do ask questions and make comments in that. And we have, I believe, Emma Shuttleworth and Tim Olcott from the Protect programme, so colleagues of Martin, on hand to answer some of your questions as we go through. The webinar is being recorded, and I'll put a link in the chat in due course to let you know where you can find that, and where you can also find the recordings of previous webinars. So the research programme, of which the work Martin will describe is part, it's a 4-year, £4 million programme, and we're carrying out novel environmental science to improve the understanding of natural flood management, where possible, including quantification, looking at a range of NFM measures at different types of catchments, flooding scenarios, and at different scales. And the aim is to improve evidence and understanding for policymakers and practitioners. There are 3 projects that make up the programme, and so that's Landwise, QNFM, and Protect. And Martin is the principal investigator, the lead for the Protect research project. So each of those project is looking at different physical geography and slightly different aspects of NFM, but working closely together and drawing together conclusions. A really important part of our work is working with partners, and without them, well, we couldn't carry out the research. And today the webinar programme is really part of that engagement with partners, trying to help build and inform, draw discussion through a community of NFM professionals. So Martin, I'll hand over to you now.
Thanks, Gerard. Thanks, Gerard. I'm going to share my screen. Can everybody see that?
Yeah, good. Yeah, can see that.
Brilliant. Okay, thanks. So as Gerard has said, Protect is 1/3 of the NERC NFM programme, titled Optimising Natural Flood Management and Headwater Catchments to Protect Downstream Communities. And what I'm going to present today is some of the empirical data that we've collected on NFM interventions in headwater catchments. I guess when this webinar was scheduled, it was probably at the point that these projects were intended to end next month. Because of COVID, we've all got a 9-month extension. So what I'm going to present to you today is not quite the final empirical data, but lots of empirical data and some of our initial interpretations of that. Protect is a big team of people that you see listed there, and as Gerard said, Tim and Emma and Adam certainly, and possibly others, are here in the room as well. So I'm not going to spend a lot of time describing the project, but just I'm hoping that some of you might have been at the webinar a couple of years ago or engaged with the project in other ways previously. But I will just give a quick summary, but I want to make sure that we have time to look at the data. So our project is mostly based around peatland headwaters and the potential for NFM benefits that accrue through the restoration of these systems. Too many UK peatlands look like this, but increasingly there's a lot of work by organisations like Moors for the Future, Myers on the Moors, Yorkshire Peat Partnership, North Pennines peatlands. A lot of this landscape is being very actively revegetated, and you can move in 10 years from the sort of thing you see on the left to the sort of thing you see on the right. And one of our core questions is, how does that impact downstream flood risk? And you might imagine that a smooth bare peat surface like we see on the left hand side creates a different catchment hydrology to a revegetated system. So that's part of what we're trying to investigate, and the key flood risk context is illustrated by settlements like Glossop, which is the small town in the left-hand image here, which is just to the east of Manchester and to the west of the Pennines. And you can see large areas of peatlands that drain down and concentrate in the town of Glossop, and that has led over the years to quite significant flooding, and as you can see in the two images on the right-hand side. So if a major land transformation is taking place in the headwaters of these settlements through the restoration of peatlands, there's potential to optimise that work to deliver downstream flood risk benefits. And that's basically what we've been looking at as part of the Protect project. As Gerard said, lots of partners in this work. It can only be done with partners at the University of Newcastle and Leeds, it's Dave Millage and Joe Holden, and key partners, Moors for the Future and the Environment Agency, who've been absolutely central in helping us to deliver the work on the ground. So the kind of analytical principle that underlies Protect is that almost all of our work is based on a BACI design, before after control intervention. So as an example, those of you that saw the seminar a couple of years ago would have heard us talking about this site up on Kinder Scout, where we have a bare peat. These are micro catchments. We have a bare peat control and a couple that have had interventions. One's been revegetated, one's been revegetated and blocked. And we study these before the interventions, we study them after the interventions, and we leave a control throughout the period of the experiment, so that we're able to exclude hydrometeorological variability, the difference between the climate in the before period and the climate in the after period, and look at the difference of the treatment catchments from the control catchment to give us strong experimental evidence of the impact of the treatments. Up on Kinder, the treatment is quite dramatic. That's Kinder Scout in 2009, Kinder Scout in 2017. That's our control catchment. So we know by studying the control catchment what would have been happening here if we hadn't intervened. I'm not going to spend much time talking about Kinder, but I just thought I'd give you a quick update. When I presented this a couple of years ago, I think we were basically showing before and after data that indicated that hydrographs moved from looking like this red hydrograph on the bare peat control through the green one when we revegetated. And if we started to, if we gully blocked and added in sphagnum, you got lower peaks and longer delays. That was, at that point, that was largely before or after data. We've now worked that out for a couple of years of extra data and for a full 10 years of individual measurements year by year. And we're looking here at lag times of the hydrographs at the top, peak discharges at the bottom. And you can see, particularly in the last 5 years, when the sphagnum went down, we're seeing continuing increases in lag time and probably reductions in peak discharge coming off these sites. And we think that's associated with increased surface roughness when you plant sphagnum into these sites. So that's an update on work that I've reported before. But what I want to spend most of today talking about is the work that we've been doing on optimizing gully blocking to try and maximize the NFM benefits of blocking gullies. And blocking gullies is a standard part of peatland restoration, but we think we can do it in ways that maximize the benefits for NFM as well. And our key study site for this has been the moors above Staley Bridge. So this is one of these types of sites that we're interested in, where the moors immediately above urban areas at flood risk. So that's Manchester that you see in the background there. This is a site that you probably subliminally know about because it was in the news about 4 or 5 years ago when there was a big fire. Oops, sorry, didn't mean to do that. And the fire is not hugely relevant to this because our site's revegetated very quickly after the fire, but it's a great picture, so there you go. What we've got up on Staley Bridge is a sort of expanded version of the Kinder experiment. So we have 4 control catchments here in red and 6 study catchments in blue. The study catchments have different types of gully blocking going in. So we've got wooden slot dams, various types of peat dams, various types of stone dams. And today I'm just going to be talking about a subset of those, the ones in red. So I'm going to talk about stone dams, which are one of the standard restoration interventions, peat dams, which are increasingly being used in headwater areas of eroded peatland systems, and some NFM optimized approaches, which are peat dams with pipes in them. I'm going to be reporting data from a before period, which was March 19 to March 20. We got the interventions in pretty much on the day of the first lockdown, and the after data that I'm going to present today runs up to the middle of the summer just gone. So we've got about 15 months of after data. Okay, so I'm going to present a series of diagrams that look like this. So I'll spend a little bit of time explaining this one. So what we've got here are plots of the, in this case, the peak discharge at our control catchment against the peak discharge in the catchment which has had stone dams in. So what we're seeing in this left-hand plot is the relationship between the control catchment and the dammed catchment before the dams go in. So you can see that they were behaving really quite similarly, as you would expect. They're fairly similar catchments selected to be so. In the middle plot, we now plot on the peak discharges from storms that happened in the after period onto the same plot. So the orange dots are the relationship between the control and the stone dams once the stone dams have gone in. And then on the right hand side, just to provide a bit more clarity on that, we're showing a residual plot, and this is the residuals of the orange dots from the trend line, which is the blue dot, the blue dashed line. So the blue dashed line is a line fitted through the before data. And so what we're seeing over here is how different the after period, the behavior of the system in the after period is to the behavior in the before period. And in the case of stone dams, looking at peak discharge here, you can see that the residuals, sorry, are both positive and negative. There's no clear pattern here, so there's nothing very obvious going on in terms of changes in peak discharge. after we put the stone dams in. Different pattern in terms of lag times. Stone dams do seem to increase lag times quite significantly once they go in. This is consistent with the data that we found when at stone dam sites on Kinderscout, where stone dams seem to have a much more significant effect on lag times than they do on discharge. So the second type of dam that we're looking at here are peat dams. So these are dams that are just created by taking a digger up onto the moor and taking the turf off the top, blocking up the gully with a peat dam, and then putting the turf back on top of it. It's an increasingly popular technique. You can see it's fairly naturalistic in the top picture there. Creates things that look like natural peatland ponds. So, you know, a popular approach for trying to restore biodiversity on peatland systems and raise water tables. So looking here at the peat dams, the impact on peak discharge is, if you look at this residual plot on the right-hand side, marginal. There might be just a hint of evidence there of increased peak discharges after the intervention, but it is very marginal. One of the things I should have said, actually, looking at the previous slide, is one thing to take note of in all of these analyses is that if you look at the range of discharges of the blue dots, which are the before period, compared to the range of the orange dots, which are the after period, we've obviously had bigger storms during the before period. So there's a big caveat to everything I'm presenting to date, that we haven't yet seen the really big storms in the after period. And in fact, we're continuing monitoring to try and pick those up. Okay, if we look at the peat dams and lag times, again, if you look at the residual plot, there are lots of positives, there are lots of negatives. I wouldn't like to claim one way or another that the peat dams are influencing lag times. Then looking at one of our catchments, which is a mixture of peat and stone dams, and there isn't really anything very surprising in this set of data. It looks quite like what you would expect peat dams plus stone dams to look like from the previous two sets that I've shown you. So we see possibly small increases in peak discharge after the dams have gone in, really no significant pattern in the lag. Okay, and finally, this is data from one of our optimized peat dams. Now, the restoration aim when you're putting in these gully blocks is to revegetate the gullies and to raise the water table. But potentially, we think you can modify some of the standard approaches to build in NFM benefits alongside that. So one of the ideas that we've explored is putting pipes into peat dams. I think you can just see a set of pipes in this one here, so that the dam holds water at lower discharge but begins to pass water slowly at higher discharges. You can see here that looking at peak discharge, the orange dots here are again the after period, and that's the first 12 months after treatment. What we did in these pipe peat dam sites is we've played around with the aperture of the pipe. So for the first 12 months, that pipe is 150 millimeters, 6 inches. For the subsequent 4 months, we stopped that pipe down to about 64 millimeters, so a significantly smaller pipe. And that period is described by the black dots. So I think you can see that once we stop the pipe down to 64 millimeters, we start to see quite significant reductions in peak discharge associated with the pipe peat dam. And that pattern shows up when we look at the lag times for the hydrographs passing through this system as well. You can see on the right-hand side in the residual plot here again, significantly longer lag times than in the before period once we stop those pipes down to 64 millimetres. So more to do here. We need more large storms. So the data that I'm showing you runs up to midsummer. We're intending to carry on collecting data at these sites pretty much through to Christmas to catch all the autumn storms, to catch some larger storms, to make sure that these effects persist in flood relevant storms. But what do we think we've found out so far? The peat dams in their kind of standard form probably have a fairly minimal impact in runoff. That's perhaps unsurprising. We need to validate it for larger storms, but all the peat dams are doing effectively is maintaining high water tables all the way through the flow line, which we wouldn't necessarily expect to impact on runoff. The stone dams, even when they first go in, do have an effect. This is consistent with what we saw up on Kinder Scout, that stone dams do seem to lead to longer lag times, but impacts on peak discharge are much less clear. And the largest impact that we've been able to generate are with our optimised piped peat dams, which are reducing peak discharge and increasing lag times once they're optimised. And clearly they are quite sensitive to the size of the aperture in the pipe. Okay, so this is largely about the empirical data, but I am going to draw on a bit of modelling here because I think this gives us some useful insight. One of the things we've been doing is using the empirical data that we measure in terms of water levels behind dams to model the flow through the dams, through the gully blocks. And here we're looking at some rather larger stone gully blocks that we've built specifically with NFM benefits in mind. So the sort of thing you see on the right hand side there. So these are 5 to 10 times the size of a standard gully block. In terms of the amount of stone they take up, they're about 1 metre high with a pipe in the middle. By measuring discharge and the stage in the pool behind these, we've been able, or Dave Millage in Newcastle has been able to validate some models of how these systems are working. And the model's based on physical principles that govern the flow of water through a permeable dam, the flow of water through a pipe, and that gives us the discharge out the bottom end. So this is work that Dave has done with a master's student in Newcastle, Amber Connolly, and looking at stage discharge relationships for a number of storms passing through these large stone dams. And here you can see the take-home message from from this is that for a number of storms, the relationship is fairly constant. The difference between the left-hand side and the right-hand side is those are the same data, just plotted log-log on the right-hand side. And this data includes really rather a large storm in October 2020, which did cause minor flooding in Manchester. So those empirical stage discharge relationships are predicted pretty well by the theoretical model. The black dots here are the theoretical model. The red is the observed data. So that's good because that means we can start to model the behaviour of these systems under different conditions. And this model simply says, OK, for a simple given storm, how do we impact the output discharge at the bottom of a system as we increase the number of dams? And this is for a given permeability. And what you can see, I think, is that as we increase the number of dams, the lag time is going up. so the purple hydrograph moves to the right, but there is a relatively small impact on peak discharge. And you can see over on the right hand side here, these are kind of two versions of the model, one that uses the theoretical model fit, one that uses the empirical model fit from the previous diagram. Either way, you get kind of 2 to 4% reductions in peak discharge, but you do get half an hour to an hour of change in lag time. And that's interesting because that's comparable to what we see in stone dams out in our catchments, that we're seeing impacts on lag time, but not so much on peak discharge. But what in a modelling environment, Dave and Amber were also able to do was to look at the impact of changing the permeability of the dam on these results. So the previous one is the permeability of a pile of stones, which is what these dams are made of. This one reduces the permeability to something more akin to gravel and sand. And you can see that what happens is we still see this increase in lag time as we put more dams into the system, but we're also starting to see in a more impermeable dam some fairly significant reductions in peak discharge. And over on the right hand side here, for different permeabilities, we can just see what the potential reduction in peak discharge is, and we get into figures of kind of 20 to 30% with 10 dams, and lag time increases that get up into the hours potentially. So the modelling data are really interesting. They identify permeability as a key control on the behaviour of these gully block systems. And that's really interesting because changing permeability potentially explains some differences that we see between different sites. So we think that from our empirical data that when you put stone dams into a heavily eroding system with lots of bare peat, the rate of change of discharge parameters in response to those dams going into the system is quicker than if you put them into a well revegetated system where there's less sediment slopping about. And that's consistent because when you've got lots of sediment, that sediment gets jammed in the pores of your gravelly stone dam and probably reduces the permeability of it. So differences from site to site based on the erosion status and the sediment supply may be down to these changes in permeability, and possibly also changes in time as progressively these gully blocks clog up. So this is something that we're kind of actively investigating at the moment. We've just completed a survey of gully blocks on the top of Kinder Scout to assess how variable this block evolution can be over a 10-year period. Kinder Scout's a good place to do this because the blocks all went in 10 years ago. There are 2,500 of them. This is our survey plan. We've surveyed 500 of them, so we've surveyed 20%. Half of them are stone and half of them are timber, and that's just completed. That data is just starting to be analysed, but it will allow us to look at whether over time we see evolution in the permeability of these systems, and we can think about what that means for NFM in the modelling framework that we just talked about. The red stars there are just the 3 long-term monitored sites that I referred to at the beginning of the presentation. Okay, so the final bit of data that I want to present relates to one of the kind of knotty questions around NFM and peatland restoration, which is how do you balance the co-benefits of the biodiversity and water table and carbon cycling drivers for restoring peatlands, which are historically the main reasons why peatlands have been restored. So you want to put the right vegetation back, you want to raise the water table, as part of raising the water table, you reduce the rates of peat decomposition and CO2 loss, and so you get carbon balance benefits. But how do we balance those kind of traditional aims of peatland restoration with the possibility that it may also be doing a job for us in terms of the NFM benefits? Critical to that is really understanding the relationship between gully blocking and water table. Water table is arguably the kind of fundamental physical determinant of the behaviour of peatland systems. High water tables lead to less carbon loss. They support kind of natural peatland biodiversity and so on. So in order to have a look at this, we've been looking at all of our sites at the impact of gully blocking on water tables. I'm just going to present data from 3 gully blocks that have been looked at in detail here by Thea Cummings, who's another master's student, this time working in Manchester, looking at gully blocks on the Staley Bridge site. And she's looked at changes in water table before and after gully blocking close to the gully, which is the left-hand side, less than 2 meters, and far from the gully, more than 10 meters away. Most of what you see in the plots that I'm about to show you is consistent with our understanding that gullies tend to impact near gully water tables rather than at a distance. That's related to the very low hydraulic conductivity of peatlands. And so you won't see much change in before and after at the sites that are 10 meters away from the gully. But you will see changes between before the gully blocks went in and after the gully blocks went in terms of the average water tables. So here we're looking at stone dams, and you can see that we shift from a water table about 200 millimeters below the surface to something closer to 150 before and after when we put the stone dams in at this site at Staley Bridge. When we put in a peat dam, we've gone from water tables about 100 millimeters below the datum to more than 100 millimeters above. So we had 5 centimeters of water table change in the previous one. We've got 20 centimeters of water table change from the peat dams. And that's what you'd expect, because the peat dams are impermeable. They very rapidly create pools that visibly bring the water table up to the surface of the peatland. And it's worth saying actually that those water table changes don't sound very much, but water tables are close to the surface in peatlands anyway, so they are significant. For the piped peat dam, as you would expect, there's a control on how high this water table gets, which is the pipe, because water begins to flow through it. But these pipes went in about 15 or 20 centimeters above the bottom of the dam, and so that is about the magnitude of the water table change that we see between before and after. So what we're seeing is positive water table effects from all of these interventions. The 2 standard interventions, stone dams and peat dams, create the lowest and the highest changes in water table. Our optimized ones are somewhere in between. So if we start to think about putting those ideas together with what we understand about NFM potential from the previous data that I showed you, it's looking as though peat dams have the maximum water table benefit, and therefore the maximum benefit for probably the carbon balance, but the NFM potential looks quite limited. Stone dams have the smallest water table benefit, but there is still some water table benefit. And critically, this is on installation. You might imagine as they begin to clog up that the water table benefits will increase. But stone dams also have some NFM potential. Pipe peat dams have a clear NFM potential if they're optimized, and better water table benefits than stone dams. So what I would take from this is that there has been a lot of rightly been a lot of nervousness from kind of restoration professionals around, if you start to mess around with our gully blocks and optimize them for NFM, are they still going to deliver all the core benefits that we expect of them from peatland restoration? And what we're seeing here is an optimized dam that sits effectively between, in terms of its water table benefits, two of the standard treatments. So I think it's encouraging that if we think about what we're doing when we optimize these dams, that we may be able to deliver all of the co-benefits that we're looking for from this type of work. So some conclusions. This is early data. We won't firm up the conclusions until the new year, at which point we will have another wet season soaked up into our loggers. But there are some clear patterns beginning to emerge from the data. There are quite different NFM benefits from the different gully blocking approaches. So if you're thinking about planning a restoration approach, it's possible to start thinking about what the likely NFM benefits are on the basis of the nature of the blocks that are going in, and possibly even to optimize those blocks to maximize those NFM benefits. We think block permeability is a really important parameter here, and the modelling work to really try and understand that and provide some guidelines on what appropriate permeability for these blocks might be is ongoing. Quite a few of the team were out in the driving rain on Staley Bridge yesterday, making one of those large stone dams less permeable by putting some plastic sheeting under the top layer of stone to try and explore empirically whether we see the enhanced NFM benefits that the model predicts if we lower the permeability of these systems. So that's a really important direction of the work for the last period of the project. And getting the permeability right and getting pipes in the right place in these interventions is critical, I think, to optimizing the block types for NFM whilst maintaining the key co-benefits. And finally, just going back to the data that I showed you at the beginning about the impact of sphagnum and revegetation on kinder, those data remind us that changing surface roughness, which slows the flow and creates mobile storage on hill slopes, is also a critical part of this story. Most of what I've talked about today has been about storage in gullies behind blocks. I think that we probably expect that the mobile storage associated with changing surface roughness will be at least as important as gully blocking. But that's one of the big questions that we expect to have answered by the end of the project. So I'll keep you on tenterhooks for another 6 to 9 months before we can say something conclusive about that. Okay, thank you. Hopefully left plenty of time for questions.
Thanks, Martin. Very interesting. Yes, that's good. I'm seeing some questions coming in now. I think people were so engrossed that it was quite quiet on the chat. But we have got some questions that some people sent in beforehand. So perhaps I could ask one of those to start with. Could you say something on monitoring habitat recovery as well as hydrology, as the two things go hand in hand?
Yes, absolutely. They do. I couldn't agree more. So we did a piece of work 3 or 4 years ago, looking at trajectories of change in ecosystem functions in response to the restoration processes, and that included things like dissolved carbon loss, but also included the runoff generation and the hydrology. And for that data, it was very clear that the vegetation change was the kind of leading driver of the hydrological change. So that was in systems where the primary restoration intervention was revegetation. Clearly, the same sort of monitoring is required for gully blocking systems, because gully blocks don't only sit there as static blocks of water, they also drive revegetation in gullies and sedimentation in gullies. That's part of what we're looking at in the kind of large gully block survey of Kinder. But I think that, yeah, we need to be understanding the trajectories of change in response to gully blocking vegetation change as well as the hydrological change. So yeah, that's a long yes.
Okay, thanks. Some questions are coming in now. Tom Nisbet has asked, did you model the effect of changing the height of the pipe in the dam and changing its diameter?
Hi, Tom. Not yet in terms of changing its height. We've played around with changing the diameter. Changing the diameter, I think, is going to be key to optimizing for flood relevant storms. At the moment, we've got quite small holes because we want to demonstrate the effect in, the types of storms that we're likely to see within the life of the project. But I think, once we can comfortably model the impact of pipe size, it may be that to protect you from the really big storms, you need a bigger aperture. In terms of pipe height, that's where we really get into this optimizing co-benefits element, because Dave Millage will tell us that what you really want is the pipe to be as low as possible. You want the permeability at the bottom of your dam, and you want it to hold water higher up. But of course, if you put the pipe right at the bottom of the dam, you get zero water table benefit. So that's a key trade-off. And in fact, the reason that I was able to show you data where, piped peat dams perform better than stone dams is because though the peat dams are more or less completely impermeable and the water table is therefore controlled by the height of the pipe, and we put the pipes in at about 20 centimetres.
Okay, thank you. Have another one of the questions that was sent in before. Could you I know you've said something about this already in your presentation, but could you say anything more, or sort of summarise the actual methods of monitoring and what key factors are important, and how you have analysed the empirical evidence?
Yeah, okay. So, I mean, in terms of monitoring, we are mostly just measuring water tables. For the discharge from the microcatchments, we measure water tables behind V-notch weirs, which are calibrated to give a controlled stage discharge relationship. And then what we do is we take those long runs of hydrological data, we extract relatively simple hydrographs, and we we characterize those hydrographs in terms of, well, a number of parameters, but the ones I was showing to you today were lag time, so the time between peak rainfall and peak discharge, and the peak discharge itself were the two that I was presenting today. So we are what I was showing you were distributions of storm characteristics taken from that data. Yeah.
Okay, thank you. And Leo Pesquet has asked, can you comment on the potential role of antecedent conditions in relation to your peak Q lag time changes for different permeability interventions?
Yes, to a degree. This is ongoing. We've demonstrated through an analysis of the before data that antecedent conditions are significant for small storms, really quite small storms, but rapidly become insignificant. And that's because peatland systems are, they're wetlands, they're naturally saturated. That's why peat forms there. So you don't need very much rain to fill up the soil profile and kind of neuter that that antecedent effect. In terms of the antecedent effect on gully blocked sites, we haven't got to that yet. That's on our to-do list. It relates really to the volume of the dams because obviously if they're all empty in a dry period and then it starts to rain, the first thing you do is you fill up all your dams. Adam Holden, who is I think on this call, is doing some work for us estimating the volume behind all of the dams at Stalybridge as part of his PhD, looking at using DEMs to do that. So we will be fairly soon at the position of being able to say how significantly important that storage volume is compared to the kind of dynamic storage that the dams create during a storm. I think my expectation is that the static storage is probably quite a small proportion of the total water that comes off in the storm, and that the dynamic effects are more significant, but watch this space.
Thanks. Can you say anything about the effect of the dams on base flows? Another question from Tom Nisbet.
Yeah, it's not obvious, Tom. We've done some analysis of this where we were trying to look at the kind of flow versus not flow over our dams, and there wasn't a very clear signal. We've got plans to look at kind of relative flow duration curves to pick that up. I mean, you would expect for the large dams, the large stone dams, the ones that I showed you the modelling of, that we would see a base flow effect, because those potentially store really quite a lot of water and then will gradually release it. Sets of small stone dams, this is kind of the same point as the previous answer really. The static storage that they hold is not probably that great as a proportion of kind of storm flow, and so presumably they will maintain base flow. But you know, base flow is a funny thing in peatland systems. It goes to zero very quickly, so probably what we'll see is that it'll go to zero very slightly less quickly.
Thanks. Emma Craig has asked, thanks for a great talk. Can any of the data collected be used to quantify the overall effect of NFM from a project or from a catchment?
Yeah, good question. That's so I've been talking very much about the empirical part of this project today, which is trying to understand how these features work in terms of the process hydrology, and understand at the small scale how that aggregates to kind of micro catchment runoff. But obviously we don't much care about micro catchment runoff. What we want to know is, if you do X, Y, and Z in a catchment, is it going to stop flooding in Glossop? So that part of the project is modelling component, which Dave Millage is looking after at Newcastle. So we are looking at 22 communities at risk on the western side of the Pennines, draining down in the kind of Manchester direction, all of which are relatively small communities at risk with large areas of moorland catchment. And what the modelling is going to do is kind of take the physical understanding that we've developed from the empirical work, apply it to scenarios of, what if we put gully blocks into all of the extant gullies upstream of Glossop, and model the potential downstream impacts. So that what you asked effectively is the end point of the project. Again, watch this space.
Thanks. Jack Dudman has said, thanks for the talk. What is the structural stability of the dams like? Might they be compromised at all by installing the pipes?
It's a good question. I don't know. They are they're about 1 metre high and they're about 1 metre wide, and they're composed of fairly large blocks of stone. We haven't done any kind of engineering analysis of the stability of them. The largest stages that we've seen behind any of them, I think, are kind of 20-25 centimetres to date, and clearly they're still there after that. It is one of the questions that we will probably look at empirically with the one that we just waterproofed yesterday. Clearly we expect to see more significant stage changes behind that one. But yeah, they're fairly hefty things. I mean, Tim is on the call and was out there yesterday, heaving those blocks of stone around. What do you think, Tim?
Do you want to come on, Tim?
I think Tim's gone for a cup of tea. Okay.
Well, I know he's been active on the chat. So
yeah, can you hear me now?
Yes. Yeah. Hi.
Okay. I'm struggling with Teams, so apologies if. Well, we haven't seen. I mean, there's two parts to this. One is the large stone dams, and the kind of physical models that Dave Millage has done for them so far as a first assessment about potential stability issues suggests that there shouldn't be any stability problems because of the nature of the material and the porosity. As Martin says, when you reduce the porosity right down, whether that makes a difference, it probably needs a little bit more. We need a little bit more comfort on that. We had actually more because of the nature of the material and the width of the dams. These are sort of 2.5 meters wide, these dams, in breadth, should I say. So they're actually pretty substantial piles of stone, which was why the kind of early estimates of stability suggest there wasn't a problem. We were actually more concerned with the peat dams with the pipe in, because these are 0.5 meter high and the pipes are about 130 millimeters in diameter. So that's as a proportion of the total height. And in peat media, we were a little bit more concerned with that. But they've been regularly overtopping those peat dams, and we've seen no changes in the structure of those dams in the year and a half or so since they went in. So we think that Dinsdale's, who were the contractors who actually constructed these dams for us, did a really good job about maintaining stability. But as Martin said at the beginning, there are this is an experiment. For wider application, we would probably want a little bit more comfort about, from an engineering perspective, about the stability of the dams under different conditions.
Yeah, I think it's also worth saying that the dams on Kinder have been there for 10 years through some really big storms, and there's I mean, to my knowledge, there's no evidence of stone dams blowing out in big storms. Various other types of gully blocking have been tried up there. Pegged down fleeces, piles of timber, and those have all blown out. So the stone is pretty stable.
Okay, thanks very much. There's an interesting question from Dick Wallace from Position Systems Limited, and he's asked, is there any mileage in making pipe diameter large and inserting an energy harvesting turbine in the case of large streams?
Way beyond my expertise, but yes, it sounds like a fascinating idea. I mean, I guess from the NFM point of view, what matters is the rate at which water is passed through that aperture. So if the turbine reduces the rate of flow, then I guess it's equivalent to having a small hole without a turbine. But yeah, I think we'd need a turbine engineer to answer that question. It would be neat, wouldn't it? Yeah. Micro hydro.
So another question now that was submitted before the webinar was, could you say something on evaluating return on investment, ROI, and risk assessment?
So the return on investment, some of that analysis was done by Dave Brown, who's our environment agency partner, particularly before the big dams went in. And the way the EA do those calculations is based on storage volumes and the potential storage, static storage that you get for the cost of the intervention. So on the kind of standard EA approach, they came out on the right side for that analysis. I think the thing I would say is that probably that approach to kind of calculating the return on investment is conservative because it focuses on static storage, whereas what we're fairly sure we're going to be concluding is that there is a significant component of what we're calling mobile storage of the kind of slowing the flow element of NFM in these systems, and that's not factored into those kind of return on investment calculations. So it's probably good that they're conservative, but I think we can probably do better than simply the static storage numbers.
Probably got time for one or perhaps two more questions. Have you, Michael Pinches has asked, have you monitored GHG fluxes from areas under different treatments, stone, peat, piped dams? I don't know what GHG is.
Greenhouse gas. No.
Yes.
No, we haven't. I mean, we do quite a lot of work on looking at the greenhouse gas balance of peatlands, and it's just not ever joined up with this project. It would be a great thing to do. I guess what I would say is that it's pretty well established that the key driver of greenhouse gas fluxes from peatlands is water table. So that's kind of partly why this kind of focus on the balance between water table and NFM benefits. I was looking at the pictures of the dam that was waterproof yesterday, which obviously created a much larger pool because it's much less permeable. Now, from a biodiversity point of view, the ecologists will love that because all sorts of bugs will live in that pool, and we'll probably get sphagnum into it, and that's all good. From a greenhouse gas balance pool, I was looking at it and thinking, ooh, a lot of methane might come off that. So it is an important question, and yeah, it would be great to be able to pursue it in a bit more detail.
Thanks, Martin. I think we've run out of time. We've covered nearly all the questions. Apologies to those of you who haven't managed to get to, but Tim and Emma have been busy answering some of the questions, some of the same ones as you, and from what I could see, you were giving the same answers, so that was good.
It's always encouraging.
More consistent answers. Oops, what have I done there? So yes, just to conclude, if I can select the right, sorry. Well, first of all, thanks very much to Martin for presenting and answering all the questions so well. I can't seem to get my presentation up, but never mind. If you do have any follow-up questions, please do get in touch, and you can get in touch with the Protect project at Protect NFM at manchester.ac.uk. I'll put that in the chat. The next webinar, our final one, is, and I've just posted a link to in the chat to if you want to sign up for that, on the 25th of November. It's on the Landwise project, and that the title is Land Use and the Management for NFM, Exploring the Evidence from the Landwise project. So I hope you will join us again for that. And we also have a newsletter. You can sign up on our website. I'll put the link to do that in the chat as well. So thanks again, Martin, for excellent presentation and comprehensive answering of a number of what I thought were very difficult questions. And we hope to see you on the next and final webinar in November. Thanks, everyone. Thanks for joining us. Goodbye.
Thank you.